Good evening, everyone. Welcome to the Kubernetes November 2020 meetup. We are back again with another meetup where we have two amazing folks who will be talking to us about two really interesting topics. First off, we have a talk from Ravi. So Ravi works at, he's a staff software engineer at Intuit, and he works on Intuit's modern SaaS platforms. He writes controllers for Kubernetes and does AWS GitOps at Intuit. He's also a maintainer of the open source project called Active Monitor, and he's a regular attendee of Kubernetes and OpenShift India meetups. So it's great to see him back. I think the last time he gave a talk was in February, and that was a really interesting talk on running Kubernetes in production at Intuit, large-scale clusters. So definitely, if you get another chance, you should look at that talk as well. So now I will be handing it over to Ravi. Ravi today will be talking to us about deep monitoring and self-healing of Kubernetes. So over to you, Ravi.
Thanks, Prakash. Hi, everyone. So start sharing a screen and then we'll get started. Can everyone see my screen? Hopefully it's yes. Yeah. So today we're going to talk about deep monitoring and self-healing in Kubernetes with Active Monitor. And as Prakash introduced, I'm Ravi Hari, working in Intuit as a staff software engineer. So the agenda for today's discussion is around the introduction of what we do, and then what is the modern SaaS platform that we have built at Intuit, and why there is a need for deep monitoring that came up, and why do we wanted to do self-healing in Kubernetes, how we can do both of them with Active Monitor, and we'll give a short demo of it. So we are Intuit, recognized as one of the best companies to work for over the last couple of decades. And then in India, we've started our operations in 2005, and we have pretty well recognized in India as well. The platform that we have built on Kubernetes at Intuit is based on AWS. So on AWS infrastructure, we run Kubernetes. Earlier, we used to build clusters with KOps. Now we started using EKS clusters. And then we also use Istio Service Mesh. And this platform is for developers' productivity. So when a developer onboards into this platform, he gets a lot of these tools inbuilt into them so that he can just focus on the code. Now, one such tool is Argo that came out of this work. And the other project that came out of this is Kiko project. I'll talk to you about those two projects shortly. And then the journey for us so far is we are having about 5,000 plus namespaces in pre-prod and close to 1,200 namespaces in prod. And we have close to 143 clusters. This was July data, but as of now, we have around 200 plus clusters that we are operating in Intuit. So Argo project is one of the open source project that came out of the work that was done at Intuit. And here there are a bunch of components. One is Argo CD, which is used primarily for deployment of applications using GitOps. And then Argo Workflows is a container native workflow engine. We'll talk about this as we go through Active Monitor because we leverage Argo Workflows in the Active Monitor. And then rollouts is for blue-green deployments and stuff like that. Argo Events is an event-driven framework that runs Argo Workflows based on the events that get triggered. Similarly, the other open source project that came out of this work that we have done for the modern SaaS platform is Kiko. Kiko project is an open source project where a bunch of independent components have been open sourced out of this, which can be leveraged to operate the clusters reliably and securely in Kubernetes. So among these components, Active Monitor is the one that we're going to talk in detail today. So before we delve into Active Monitor and other things, let's understand why we need deep monitoring in Kubernetes, even though we have tools like Prometheus and other monitoring tools that are available in the open source, right? So the monitoring that generally we do is around the resource utilizations or the number of pods that we are running and other things. But a deep monitoring in Kubernetes is needed when we want to know whether the controllers that we are running, for example, a kubedns controller or a core DNS controller, is it working and it's doing its functionality right or not. There could be many possibilities that a go routine in the controller may be killed because of a number of reasons, and we see that the controller is still in the running state, but unfortunately, the actual functionality may not have been executing. Right. In that case, it's our responsibility to validate that functionality by exercising a monitoring, coroutine and ensuring that the whole functionality of reaching out to the external domain from inside the cluster is actually working, or we can also ensure that the DNS internally in the Kubernetes also works fine by reaching out to other services and stuff like that. Now, the other thing that we would usually do is connect to external resources like AWS. Uh, we also we use controllers like KAM controller, where we connect to the AWS resources from the KIM framework, and then we need to exercise that functionality to ensure that our connectivity to AWS infrastructure is working fine. We also need to check whether we are reaching our limits or not, right? We use a lot of resources on AWS, but there is a limit to all the resources that we use based on how much we pay. Now, it's always a good idea to keep in check whether we are reaching that limit early in hand rather than worrying about and handling things at a later point in time after we hit that limit and there is some issue in production, right? So if we know early in hand, hey, we're reaching certain limit, we could go and fix that or increase the limit or whatever the action that we want to do. So all these are just few use cases, but there can be many more such use cases, and all these different cases made us think that it's not enough, and all these different things are not monitored, by any open source tool at this point. So we thought we'll go ahead and build a controller for it that does this monitoring for us, and that could exercise these functionalities and ensure the Kubernetes operates the way it is expected to operate in our given environment. Now, why do we need self-healing, right? So we saw the use cases for deep monitoring. Is monitoring not sufficient? Monitoring is sufficient for us to know that there is a problem, right? When there is a problem, we get alerted. But in our practice, what we have learned is that most of the times, whenever an issue happens, we just go and restart the pod, or we just go and do some quick fix that doesn't have to be always a manual effort involved in that. It could be automated. Now, based on our experience, some of the use cases for that where DNS pod, for example, is in a crash loop backup state. It went into that state probably because a health check failed on it, or something, a network issue happened at a particular point in time. But by the time when we go and check it, that issue might have gone away. So all that we had to do at that point was just restart the pod, and then it runs fine. And this is a common case, I believe, across many organizations or many Kubernetes clusters, where at some point in a random interval of time, the pods may get into some bad state, and all that we had to do at that point was just restart the pods, and things would work fine. For that, we don't necessarily have to invest in a human in that, right? So we could simply automate the task and run that and heal that for us. Now, the other use case could be, as we discussed, AWS limits has reached. Now, if we already know that we are reaching that limit, we can early in hand call an API to increase the limits, or we could delete the instances which are not in use, or say some ASG launch configurations which were old, which were not active now, we could go ahead and clean them up so that we get more buffer space or limit for us, right? So all these different use cases will come up. Similarly, Prometheus storage volume, if we do not need older metrics, we could go ahead and clean them up. Instead of monitoring only doing the actual monitor, we can also add an additional layer of self-healing to it, and then clear that problem away for us. There are other use cases like if a pod is going high on CPU or memory, or a JVM in a pod is consumed more, and you may run diagnostics before actually deleting the pod, or before actually fixing the problem. You can run the diagnostics, collect some information, push it out into an S3 bucket or something like that, and and then do the self healing. So these are the use cases that led us to believe that it's actually very efficient if we do self-healing in Kubernetes along with monitoring. That way we can fix the problem as we know the pattern of the problem and stuff like that. Now, how do we do this self-healing or remedy, right? So there could be a controller which we could write something like this, right? Where we can say kind is remedy, and then we could query Prometheus in that. And then if it meets a condition, let's say here this condition is if the memory is greater than 95%, we could go and delete that particular pod by giving a specific remedy action. Let's say if we run this, we could run into, because when we describe the CR, we could see something like this, like it met the criteria that it failed, and the threshold is 95, but the value is at 99%, and so it went ahead and deleted, and that's a successful case. Now, this is just one use case, right? Now, what are the problems if we implement a controller that solves every use case like this, right? So one is, in order to scale our controller, we need to implement every use case by ourselves. In the sense that our controller should be able to do handling of these use cases, which may take time. It's not that it's not possible, which may take time. But when we put it in the open source, there could be n number of use cases that we don't know of. We may, the users who are using these controllers, they may not have their use case already built in the controller, right? So they may see that it may not be an efficient time investment for them to use a controller. Rather than that, they can build something on their own. Now, that's a challenge for us. So users should essentially have the ability to define a use case and have a remedy action also defined by themselves. Instead of building that piece of code into the controller, they should be able to write that use case, and they should plug in that into the controller, and the controller should be able to execute such a monitoring and self-healing use case, right? So for that, we leverage something called Argo Workflow. As I was telling earlier, Argo Workflow is an open source container native workflow engine for orchestrating parallel jobs in Kubernetes. So when we submit a definition of workflow to the Kubernetes controller, it runs these jobs for us, and then it responds back with the status of whether that job is successful or not, and other things. So Argo Workflows is what we started leveraging, and that came to the rescue of solving n number of use cases that we could think of. So essentially, what Active Monitor is that it's a Kubernetes controller, and it's built with KubeBuilder, and when we submit a custom resource definition to this controller, it launches an Argo workflow, and that Argo workflow can monitor either AWS, or it can monitor a Kubernetes resource, or stuff like OPA and other things. And then once it runs that Argo workflow, we collect the data, that is a metrics, and then send it over to Prometheus. From there, you can send it to any other long-term storage, like a Wavefront or any other stuff. So essentially, this is what Active Monitor does. Now, how do we achieve self-healing with Active Monitor? So as we have seen, we submit a definition for custom resource. Now, as a part of regular monitoring framework of Active Monitor, it goes and gets the data from these different sources, right? Now, it checks whether the health check that we have run is success or failure. then if it is not a failure, it will go ahead and continue executing it after a certain interval of time. But if it is a failure, it will go ahead and execute a remedy workflow. So we submit two workflows. One is a monitor workflow, which continuously executes at a specific interval of time. If that monitoring workflow fails, then it executes a remedy workflow, and then we collect the metrics out of it after the remediation happens or self-healing happens, and then we update the status back in the custom resource, and then run the health check again, because we know that the issue has fixed. Ideally it should keep monitoring, and it should not happen. But if the issue happens again, we run this remedy and stuff like that. We can have a limit on how many times it should run, and then send the data out and other things, or raise an alert. But in the first place, if we know a pattern of the issue, we do not have to wake up a human being and run the remedy workflow.
I think we lost Ravi. I'm not sure. So let's give it a bit of time. I think it's about 7:16. Let's wait for 2 minutes. I think due to network connectivity issues, Ravi dropped off. So in case he is not able to join us in about a minute or two, we can move ahead with Nurain's talk, and then later on get back to Ravi's talk. I think he's back. Yeah, Ravi. So you're
Sorry, there was a. I'm sorry. Where did you lose me?
yeah, we lost you. I'm not sure. Can you pick off from the slide on design for self healing?
Sure, I can start it from here again.
Sure. Not problem, Ravi. You can share your screen and add it to the stream. Ravi, are you around? So I think we lost him again. So I think we can move to our next talk, and we can come back to exactly where Ravi Ravi was later. So let's just give him another minute to get back.
Oh, hey, you just put me on the screen. Hi, everyone.
So I guess we can move on with the next talk, right? I think Ravi is dealing with a persistent network issue. We lost him twice. So I see him. I see that he's back. Let's just check. Ravi, so will you be able to continue, or do you need a
Yeah,
while to? Will
I
you
think
be?
whenever I'm sharing something, it's breaking the network. But let me try one last time.
Sure. Can you share your screen, Ravi?
Yeah, I'm starting. Can you see my screen?
Yes, we can.
Okay, cool. So I'll start from the active monitor workflow, self-healing and design again. So as we have seen here, the controller essentially submits a workflow job, and then the workflow triggers for the monitoring part. Now, how do we achieve uh, monitoring and self-healing? Is we submit the CR along with the active monitoring. We also submit the CR for the workflow. Now, the workflow starts executing. First, it executes a monitoring workflow, and as long as the monitoring workflow runs fine and there is no issue, it keeps on executing it. But when there is an issue, it triggers the remedy workflow. It will trigger the remedy workflow, and then remedy workflow gets executed, and then the metrics gets collected, and then the status of this remediation gets updated. Then it triggers the uh, deep monitoring or the active monitor workflow again, just to monitor. As long as the monitoring is fine, we don't trigger the remedy workflow. So this is how it works. And as we have seen earlier, it goes and it can query the data from any endpoint that is exposed to it, or any other CLI commands that we can run internally inside the workflow. Let me share with you how a workflow looks like and give you a quick demo. Let me switch to different share. So this is how an Argo workflow would look like. So an Argo workflow essentially consists of basic definition of what we want to do inside that workflow, right? But as for every custom resource, we need to submit the kind, which is a workflow, and then the API version that it needs, and then some metadata. The generated name can be anything that we want. In addition to it, there will be a random number that gets added to this. And whenever the Argo workflow pod gets generated, that workflow pod name will be prefixed with this generated name. Now, the entry point here is, we'll say, when we say this entry point, that means the template which we have with the Argo workflow will run this. And then the container that we use is this one. So this container, I've given an example of how to use this when we run Docker and stuff like that. It would go ahead and execute the operation. But in actual production workload, this is completely different on how do we operate the containers and stuff like that. This is just an example of how we can run a container in the Argo workflow. Now, here we just pass the command, which we actually pass to the Docker like this. We have to pass a command to this image, and then arguments for this as we give in the Docker hello world. We are passing the commands in the arg section in the Argo workflow definition. We can also give the resources that we want to pass to this specific Argo workflow. So this is how we can build the Argo workflow. Now let's see an example of how we actually use this Argo workflow to monitor DNS is whether a DNS is working or not in our Kubernetes cluster, right? So in Active Monitor, what we have done is we have wrapped up Argo workflow on Active Monitor, right? That is Active Monitor, as we have seen, it launches an Argo workflow pod and executes the Argo workflow. So basically it coordinates with that Argo workflow controller. Now, when we submit the definition for the Active Monitor, essentially it's a health check controller that we define. So the kind is health check, and the API version is this one. Similarly, we pass in the metadata for it, in which namespace it has to execute and stuff like that. The repeat after second interval is how frequently we want to run this monitoring. As we have seen earlier, we can run this monitoring every few seconds or every few minutes and stuff like that. We can just define what is the interval at which we want to run. And then we can define the level. When we say level cluster, all the RBAC permissions that are necessary for this monitoring to run at the cluster level are given. That is part of the controller code. Now, when we say a namespace, for example, I can write another definition where I can give the level is namespace. When we say a namespace, the pod, the Argo workflow pod that runs, it will only have the permissions to execute any operation inside that namespace. It will not be able to reach out to any resources outside that namespace. So we can choose which kind of permissions we want based on our desired monitoring that we want to do. Here we pass in the resource definition, the resource name namespace we pass, and then the service account. So this service account will actually get all the permissions that are necessary for this monitoring workflow to execute. And then the Argo workflow, we pass this as an inline definition. So the definition that we have seen earlier is an example earlier here. We have seen as an example of how to write a simple hello world using a Docker image. But in order for us to write, say we just want to run NS lookup, we can use some DNS utils image and then run the NS lookup on google.com and ensure that from inside the Kubernetes, we are able to resolve to the external domains outside, right? So these are ways where we can define the monitoring workflow. I'll show a demo of this as well as we go through, but I'll just show you how remedy workflow can also be embedded into the active monitor. So we have seen that, this is the same similar definition that we have for DNS, but here what I'm checking is I've written a custom image of mine where I'm kind of launching a stress pod, where in that particular pod, this is a stress pod definition where I'm in that pod, I'm running, eating up all the memory and stuff like that, right? So the monitoring definition here is it will go and check in the Prometheus that is running in the cluster for this particular namespace and this particular pod on this container, whether the threshold is reached or not. 95% 95 is the threshold. We can choose whatever value that we want. If I pass these different arguments, it will go and verify by querying Prometheus whether that particular pod memory has reached 95% or more or not, right? So this kind of images is something that any end user can build on his own. They don't have to limit themselves to the use cases. They can write their custom use cases. They just have to have a Docker image for it, and they can embed that into the Argo workflow and run it. Now, this is the definition of the remedy workflow. This is in parallel to the workflow that we pass for the monitoring, right? So in the remedy workflow, what we pass is the action that we want to do to remediate this problem, right? So the action here that we are defining is delete that particular pod. Whichever crosses 95% of memory, we don't want to run into a bad state for an application. So we can also include some diagnostics if we want, like take a memory dump or collect some statistics and other things, or take some thread dumps and other things, and then push it over to an S3 bucket and then delete the pod. We can do all that stuff in the Argo workflows. So here, the step that we are doing here is only deleting the pod if it reaches 95% memory usage. So let me quickly show you that demo. So this is the definition that we have seen just now, like it runs the NS lookup and stuff like that. And yeah, so for example, here, if we are running this pod, when in the controller that is available in the Kubernetes, we just have to submit this workflow, the inline DNS.yaml, which is what we have seen earlier and walk through the definition. As we submitted it, this gets submitted into the Kubernetes. That particular custom resource definition is submitted now. And if we go and check the health check status, we see that this particular health check is running and it is succeeded. So if we go and look for the pods, there is one pod that got created, and that pod is in a completed state. We can check the logs for this pod and see what has happened inside the pod execution, right? So this pod here clearly logs that the google.com is reachable, and it throws this address of this domain. The IP address is what it throws. So essentially, this gives us confidence that hey, our DNS resolution is working from the cluster. Now let's look at the remedy example, right? So this is a remedy definition that we have seen earlier. So I'll quickly fast forward this one. So again, one of the things is we can choose to use the same service account in the remedy workflow if that has enough permissions. But usually what happens is when we monitor, we don't give write permissions on resources, right? So we just give the get permissions or read permissions and stuff like that. But when we have to run the remedy, we may have to delete the or we may have to update and other things on particular resources in Kubernetes. So we will have to pass those permissions. So when you run a remedy workflow, it is always a better practice to use a service account, which is different from the monitoring service account. If you do not mention this, default the service account of the monitoring gets used. And we update the permissions and other things for this the same way. So now what I'm doing is I'm going ahead and creating a stress pod in that namespace. That way this pod consumes a lot of memory so that we can run our remedy workflow and see whether it is actually working or not. So this pod gets created, and we can see that memory demo pod has been created in that namespace. Now we go ahead and run our remedy workflow. The memory in the pod increases gradually. That is, it starts eating up the memory slowly. It doesn't eat up in the first time. So as you see, the first time when the monitoring run, it is succeeded. That means there is no failure. The memory did not exceed 95%. So we can see the logs for that monitoring pod that was launched. When we see these logs, we'll see that the memory usage must have been less than 95%, and as it says, it is only 17%. But by the next time when we launch, it may grow up. The memory may grow up, right? So instead of waiting and other things, what we could do is we can delete this and launch another workflow. Or we could just wait for the time until it gets that failure and then triggers the memory remedy workflow. Now we have launched the health check CR with remedy again. Now, as you see here, it actually fails because by this time the memory demo pod would have already reached the memory limit that is greater than 95%. As you can see here, the memory usage in this particular pod is now 99%, but the configured threshold is 95%. So one other important thing is we have used a retry strategy limit of 2. That means it tries 2 times. So that's why you see that 2 memory workflow pods are generated. In the Argo workflow, we can define the retry strategy limit. We can run it as many number of times before we confirm that it is actually a failure, right? It could happen that at times, all of a sudden, the memory could spike up. Then you don't want to immediately take a remedy action. You might want to wait for a few more minutes and then check if that if that memory is still high, and then you may have to do the remedy, right? So all that you can configure in the remedy workflow, in the monitoring workflow. Now the remedy has triggered. So let's see what the memory has done, right? So the definition that we have given for the remedy workflow is to delete the pod. As you can see in the logs that it says that the pod has been deleted. So this is how we can, execute and achieve our monitoring and self-healing. Now, as you can see, we have updated the status back that it failed once because we have relaunched it again. It failed once, and then the remedy succeeded. So it will rerun the rest of the process again. So this is how we can execute remedy. I'll share how we can run this project in our local. So all that you need to do in order to get this project is go to Kickoff Proj Active Monitor, and you can just get the GitHub link, clone it, and then once you have it in your local, you can open it in your favorite IDs. I'm using Golang here. You can just run make run in this project. It will launch the controller, and then once you see this, the worker count 10 line, that means the controller has launched. And then let's see, the context is at Minikube. We can run some examples. Let me see if there are any health checks. There are no health checks that are defined. So the alias I have defined is KH is kubectl minus n health. So now we can go ahead and launch a workflow, say, or we can launch the same one in line DNS, right? So this gets created. So this is a health check CRD that gets created. When we describe this, it has already completed. So basically, when we describe this, we'll know that this is a last workflow that got executed. And every 60 seconds, this gets executed. And the workflows that have already been executed, they get cleaned up after a certain interval of time that we can choose based on the total time to live and other things, the configurations that we can pass. Otherwise, default, it will be 30 minutes. After 30 minutes, all these get deleted. So when we see, so this is the part that that it got launched and it completed. We can look at the logs, which is what we have seen, right? We just have to remember that workflow.
Just
Yeah.
wanted to see, we are not seeing any updates on the screen. So are you sharing another screen or something?
Sorry, let me share my screens. I'm sharing my entire screen. Let me know once you can see. Can you see my terminal?
Yeah, now we can see your terminal.
Okay.
Yeah,
Sure.
so all of that was lost. Sorry.
Okay, I'll just repeat that. It's not a big deal. Essentially, you have seen. So basically, what I was talking about is, in order to get this project, you just have to go to this Kiko Active Monitor, get this project either through SSH or something like that, clone it, open it in your IDE, and just run the make run command. And once you do the make run, it will launch the controller. You can see my IDE and other things, right? Okay. So basically, it launches this workflow controller or health check controller, and then we can submit the workflows as we have seen earlier. Here, let's say I'll submit workflow. So if you see, there are two workflows now. The earlier one was running, and this is a new one that I launched. And let's see if this pod got created. So this got created. So you need to remember that in these pods, which are launched by the Argo workflows, these are called workflow pods. They also have a sidecar called wait container. We have to, if we have to check for the logs, we have to look for the main container. So as we have seen, the Hello World workflow, this just prints out. We could also get the logs for the DNS workflow pod, which we have run earlier. Yeah, so this is how we run the DNS workflows or any kind of workflows that we want. There are a lot of examples that are given out for you to try out and see whichever one we want to use. You can also define the definitions of the repeat after seconds using a cron job. Some of the definitions are shared here. I mean, how you want to use is up to you. You can schedule either using a cron job, or you can pass in a repeat after second interval and other things. So you just pass in this workflow definition for your monitoring thing, and it does the monitoring for you. And similarly, if you want a remedy, the examples are given in the remedy examples. You can see this one, the one that we have used. So if you want to build for your specific use case, all that you need to build is a Docker image and put that out into the workflow. It'll do the deep monitoring as well as self-healing for you. That's pretty much what I had. I'll take any questions.
Yes. So that was a great talk. We have some questions flowing in through the comment section. So I'll bring them up on the screen here so that you can see it as well. And then we can take them one by one, right?
Sure.
So, and also for those of you who have just tuned in, you can put your questions in the comment section and we'll address them one by one. So first one is by Suraj. It says, can we monitor if two pods can't communicate to each other?
Yes, we can do that, because you can launch with the latest Kubernetes versions. You can launch a debug pod inside, inside a regular pod as a sidecar, and then check whether that particular pod can communicate to the other pod or not. That is one way. The other way is you can launch a pod in a particular namespace and then check from that particular namespace whether you're able to communicate to the other pods that are running in a different namespace, right? So there are multiple ways you can do that.
Also, there's one by Ranajit. So he is like, are these kind CRDs?
Yes.
I mean, the
So
workflow and
right. So workflow is one controller, and active monitor is another controller. So we have embedded Argo workflow in the active monitor controller. So these are different CRDs that are put together.
So the next one's by Anthony.
Mm-hmm.
He says, shall we create all those kind of workflows in Jenkins? So why do we need to use Argo workflow?
So Argo workflows provide you a cloud native way of doing things much smoother. When you run it with Jenkins, what happens is Jenkins will be run usually in a separate environment, and you need to have appropriate permissions, and your security and all those things have to be cleared to be able to execute something on a target cluster. But if you use Argo workflow, that can be installed in that particular cluster itself, and because you're running it as a controller, it can be run in the cluster, and it becomes much easier for you to handle things.
So the next question is by Giri Prasad. So he's like, can we access the sample somewhere to run on our local cluster?
Yes, you can. All the samples that I've shared are available in the project repo in the examples folder. You can use them and try it out in your local clusters.
And also, if you can post it onto the Meetup page, we will post it onto the Meetup page, all the links,
Yeah.
and we will tweet it out as well. So you
Sounds
can just follow us on Twitter. I'll put up the Twitter handles later, so you can follow all the updates over there. So the last question that we'll be taking is by Anthony again. So he's like, Argo workflows, is it in production support? Does it have production
Yes,
support?
Argo Workflows is used pretty widely by Google for their Kubeflow engines and stuff like that. And we use it in production for machine learning pipelines as well as for our regular monitoring workflows and stuff like that. So it is production ready.
Yes. So we've got another minute, I think. So if there are no more questions, I don't see any more questions here. So
Maybe I'll
yeah,
say that if you like this project, go ahead and give it a like on the GitHub repos and reach out to me if you have any questions on this.
definitely. So if that's all from you, Ravi. Thank you so much for doing this, and thank you so much for being here and sharing your knowledge with the rest of the community. We always appreciate people coming forward to share knowledge with us. So it's great to see you back. You're a regular Meetup member as well, so it's great to see you back. So yes, thank you so much, Ravi.
Thank you. Thank you. It's been a pleasure. Thank you for inviting me. Thank you. Bye.
So next up is Nurain. So Nurain works for Space Up Tech. So he works on a product. He's the founder of Space Up Tech, and he works on a product called Space Up Cloud, Space Cloud. And yeah, so today his talk will revolve around the project Kubernetes Event-Driven Autoscaler. So he'll be talking to us about that, and I'll leave Nurain's introduction to Nurain.
No, but I think that was good enough. So yeah, thanks for having me over. It's really a pleasure to be back. And yeah, today I am going to be talking about event-driven autoscaling. Like Prakash mentioned, I am the founder at Space Up Technologies, and I'm all things into cloud. So, but before we start, if you have any questions during my presentation, feel free to drop them in the comments. I am monitoring them, so I'll be able to take them as and when I feel they are relevant. Also, I'm going to be talking about a tool called Kada, but I won't be diving into the technical details of it. I really want to focus this presentation on, I would say, on the use cases where Kada really shines, and why I think that every Kubernetes cluster needs to have Kada running on it. Okay, that's a big claim, but yeah, let's just see it. So who I am? Let's start with that. I'm Nurain, your tech bud, on Twitter, and hopefully, if this presentation goes well, in real life as well. So as again Prakash mentioned, we are a company backing an open source tool called Space Cloud. Now, if I had to describe Space Cloud, think of actually imagine Google Firebase. Okay, imagine Google Firebase, and imagine now Google Firebase can work with all the open source databases out there. So it can work with MongoDB, MySQL, Postgres, and think that it can even perform foreign keys and joins on those databases, and has a GraphQL layer on top of it. Doesn't end there. Now think of the experience you normally get with a tool like Heroku, right? But the scalability and power of Kubernetes, right? Merge this Firebase angle with this Kubernetes angle together, and the recipe you get is Space Cloud. I know that's a mouthful, but that's what it is. And obviously, if you wanted to add some icing on the top, yes, whatever I'm going to be talking about, including Kada and Space Cloud, is completely open source. So it's not just a sprinkle of icing; it's kind of the entire thing being icing, because almost everything is open source. I just ruined the recipe, right? Let's just move on. Okay, so first let's just set the context. So I'm just going to be talking about a use case we came across when dealing with our clients, and The reason why I'm picking this up is because I think it's broad enough that most of you would be able to relate with it. And it's pretty simple if you think about it. So we have an AWS setup here, right? And the customer we were working with, they had a ton of events being generated, some directly from the database, some were external, some were even internal events. And all of them were being queued in SQS, like the Amazon SQS, the simple queuing service. Uh, and from there, they were triggering Lambda functions. So all the events always went to SQS first, and obviously Lambda is invoked automatically whenever you can configure Lambda in that way. Now this solution is really elegant because there's absolutely no infrastructure which is being managed. Everything is a managed service. As you know, like if there were no events in the queue, there would be no invocations of AWS Lambda happening at all. And that's a big cost saving if you think about it, especially for this use case, because the nature of these events was such that they were sporadic. As in, these events are not happening throughout the day; it's happening in pockets. It may happen throughout the day, so we really want to conserve on resources when events are not happening. Uh, and the best part about this, obviously, because we're talking about auto scaling, is that Lambda is known to really scale really, really well, right? Uh, so this was seemingly perfect. But the problem which came up was that AWS Lambda was kind of becoming a little bit restrictive in the sense the execution time is kind of limited, and they wanted to use some dependencies which they were not able to import in Lambda. But the bigger concern was that this currently a SaaS offering had to be deployed on their customer side as well. So they were going product based, and because of that, they also had to deploy this entire system of theirs on the client's premises. So which could be AWS, may not be. It could be another cloud provider. It could even be a private cloud. Like a traditional data center kind of architecture, right? Uh, and Lambda and AWS is very proprietary in its nature. So I think that was the biggest issue why they wanted to really move away from it. Uh, Now, actually, if you think about it, the replacement for this is fairly simple. And since we wanted vendor agnostic attributes for our system, we obviously chose Kubernetes. And the reason Kubernetes really works is because most of the cloud vendor have a managed offering wherein you don't really have to worry about the underlying nodes. And since you're not worrying about the nodes, it gives you kind of a serverless feel, or at least it reduces considerable DevOps burden from your team, right? Uh, and for instead of SQS, we chose RabbitMQ. Uh, Now, the decision to choose RabbitMQ is completely arbitrary. It could have been Kafka. It could have been, NAT streaming. It could be any durable, persistent pub subsystem. So we're just using RabbitMQ because they had a personal preference to it. But you might as well swap it with any other system. And because now we don't have Lambda, we could have obviously gone on for a FAS, like a function as a service on top of Kubernetes, something like OpenFAS or Fission. But then we did not really want to restrict ourselves to the same kind of execution time limits which we were getting on AWS, like on Lambda. So we thought, like, hell, why not microservices, right? Uh, but I'm not really going to focus on the remaining pieces. I really want to talk about auto scaling. And the only way we could think of to auto scale these microservices back then was using the horizontal pod autoscaler. Now, Kubernetes has this really cool construct called the HPA, right? Wherein you can just define what kind of average utilization do you want on your pods in terms of CPU and memory predominantly. There are some other metrics as well, but that's not really used a lot. So we'll stick to CPU and memory. And then based on that, Kubernetes would automatically scale your deployment or your stateful set. And I'm pretty sure you know about it. And it sounds good, right? So, I mean, as the load increases, as more and more events get queued in RabbitMQ, more and more events would get processed by the microservices, and their CPU utilization would rise as a result of it, and HPA would kick in, and things would auto scale. Sounds perfect. Um, Not really. Obviously, if it was supposed to be this small, you'd think I would really end my presentation on the fourth slide. No, there's more to it, of course. We cannot simply use HPA for such use cases. Okay. And let's just try to take them one by one. So the core the core aspect here is that just scaling based on CPU and memory isn't enough. You cannot just scale on CPU and memory. It just doesn't work. And the reason is because many people still use JVM or VM based languages. And one of the properties of these VM based languages is that they hog resources upfront so that the application doesn't have to wait for the heap space to be allocated. Like JVM really does this, right? It's going to go ahead and hog up all the RAM memory so that your application doesn't have to when it really needs it, which is good for your application. But then your autoscaler is getting wrong information here regarding the memory utilization, because it's JVM just hogging it upfront even when there's no load as such on it. And again, many event loop frameworks, especially in the C ecosystem, they kind of hog up the CPU upfront as well. But this is not just the only reason why CPU and memory is a bad fit. When you're using something like a PubSub system, you have a cap on how many messages your microservice is going to be processing at any given time. You don't want to keep it uncapped, because what will happen is, suppose there's a sudden spike in the events being generated, all those events would be sent to your microservices, which could get overloaded and crash. So as a best practice, literally everyone using RabbitMQ or Kafka NAT streaming, they kind of put a cap on how many messages is going to be processed by your microservice at any given point of time. And that cap is hard. It's enforced technically by RabbitMQ. So RabbitMQ wouldn't even push messages if you've already hit that cap. Now, what that means is the number of messaging being processed by each instance of the microservice is capped. It's limited. It's not going to go beyond a specific value. Let's say you don't want to process more than 10 requests at any given point of time, so that it will never go beyond 10. And this means your CPU utilization or your memory utilization also is kind of going to get capped around that point. So even if your events keep coming in, right, even if the load generated because of this events is high, RabbitMQ is simply going to buffer them and not give it to your microservices. And because the HPA doesn't really understand any of this, it's just going to wait for the CPU utilization to bump up, which probably wouldn't, because you've already given enough CPU resources to your pods, to your microservices, so that they don't have to, they don't peak the CPU at all. Now, that's a big problem. Another one which I really think is important is that when you're scaling based on CPU and memory, you cannot really scale down to zero. Like, think about it. If there are 0 instances of a microservice running, the CPU utilization obviously is going to be 0. Now, even if events are coming in, your CPU utilization is still going to be 0. So there's no queue for the HPA to scale it up again. And it's technically impossible to scale up from 0 when using HPA and scaling based on CPU and memory resources. So we kind of losing out on a lot, and that scale down to 0 was an important factor, because we do not want all the microservices to be running all the time. So what do we do, right? What we really need to ask is, what do we want? And what do we want is ideally not scale based on CPU at all now. We do not want to scale based on CPU or memory. Instead, we want to scale based on the queue size in RabbitMQ. Let that sink for a bit. So what I'm trying to say, as messages is coming into RabbitMQ and filling up the queues, the queue length is obviously increasing. The queue size is obviously increasing. We want to scale on that. So if the load was high and the queue sizes was increasing rapidly, now we know that, hey, the scale is suddenly, turning up a notch, and we need to add new microservices in place. And this seems to be a far closer metric, or should I say a far truer metric than CPU, because CPU is a consequence of your load. It's not the root cause of the load. The root cause of the load being exerted is because the events which are being queued inside RabbitMQ. So we really want to scale based on the queue size in this particular use case, right? And yeah, this is precisely where CADA comes in. And So just to be clear, CADA does not replace the HPA. So many people have this misconception that CADA is replacing HPA, which is such a battle-tested construct in Kubernetes. Actually that's not true. So what CADA really does is it continues to use the HPA, the horizontal pod autoscaler. But what it does it adds a whole slew of metrics on top of which HPA can use to scale. And not just that, it kind of extends HPA to scale down to 0 as well. So HPA would be responsible for scaling from 1 to n and n back to 1. But the scaling down to 0 and scaling up from 0 is handled by CADA in this case. So really, CADA is trying to reuse most of the HPA code, most of the HPA functionality which is there, but just add or augment its functionality by a little bit. And because it's such a thin layer on top of it, it's a very lightweight tool. So CADA requires very less resources to actually run. And that makes it a very silent observer. And another big part is, so if you're already using HPA or things like that, adding CADA is not going to disrupt anything. So you don't have to reconfigure RabbitMQ, or you don't have to reconfigure microservices. It just plugs in. It's non-intrusive. So I just wanted to keep that in mind, because there are some misconceptions around CADA that you have to rework your services and rework your architecture in order to use it. But that's not true. CADA will plug into your architecture without having to change anything. And what I really love about CADA, apart from adding scale down to 0 functionality, is it's got a hell lot of autoscalers built into it. Let me just give you an idea of what I'm talking about here. So this is the CADA website. Okay, now if I do the drop down on scalers, you can see. Okay, actually, you know what? Let's just hide this. Yeah, you can see there are a bunch of scalers. Half of them, probably I've not even heard of them. And it doesn't end here. So if I click and I go in, there are way more autoscalers in here. You can literally scale based on RabbitMQ queue size. You can scale based on Kafka, the pending messages in Kafka. You can scale based on NAT streaming, but it's not just limited to pub/subs. You can even scale based on results obtained from certain system, like scale based on the result from a Postgres query, from a MySQL query, from a Prometheus query. You can even scale based on cron job. So, you can preemptively say that Friday mornings is a peak load time. So let's just scale preemptively before even load touches your system. So the whole slew of autoscalers in CADA is incredible. I know you're not going to be using each one of them, but in any one of your application, you'll probably touch one, at least one. And using CADA doesn't mean you're foregoing scaling based on CPU or memory either. You still can scale based on CPU and memory, but you get all of these different scalers, as an add-on to it. And CADA version 2, which just got released 2 days back, has also added support for adding multiple triggers. So you can scale based on CPU and the queue size if you so wish to. You can absolutely do things like that as well. So let's go back to the presentation. And yeah, so that's the major advantage of CADA. But then, of course, CADA doesn't have autoscalers for each and every tool. Perhaps you have an internal metric system which you want to use, which is not really in Prometheus, or it's more proprietary. It's very easy to even add your custom metrics to CADA. It's a very small piece of code, probably within 100 to 200 lines. You're going to fit it, and you will be able to add a custom scaler to CADA as well. So the end result looks pretty much what we wanted to. There are no changes in the architecture. I can use RabbitMQ exactly the way I wanted to. My microservice undergoes no changes whatsoever. Just a CADA gets added as as a Kubernetes controller, which is running. It has its own CRDs, and it's monitoring RabbitMQ's queue size for you, making it available to the HPA so that the HPA can scale on the queue size rather than the CPU. Yeah, it's that simple. Trust me, scaling based on CADA is actually that simple. So if I really go back to my RabbitMQ queue size, right, and I say, how does the specification look like? it's as simple as this. You define a bunch of triggers. You mention the type, and in this case, it was RabbitMQ. You mention your RabbitMQ connection string. You can even pick it up from an environment variable if you wish to. The protocol to be used, the queue length. This is the ideal queue length you want to have per replica. So if there are 21 messages in the queue, you're going to have 2 replicas. If there are 40 messages in the queue, no, like 42 messages in the queue, you're going to have 3 replicas. It's as simple as that. And actually, that's it. There's nothing fancy to it. So, okay. So now what? Uh, so when we really started using Cater, it felt really nice. We knew we want to use it, but then something was missing. Something was missing, which is very true when you're using Lambda. And once you're using Lambda for that use case, it's very difficult to get out of it. And that bad news is that Cater doesn't really support scaling based on incoming requests. So you cannot scale based on the incoming request. So things like what AWS Lambda does really well, like replace SQS with an API gateway. And what you could do is, like, based on each incoming request which you have, you're spawning an AWS Lambda function. And you probably want that for your services as well. Because if there are no incoming requests in your system, you probably don't want a single instance of that service at all. You probably want to scale it down to 0. But yeah, Cater does not support that use case. And it kind of makes sense, because what Cater really doesn't get into is buffering those requests. So if you might have noticed that if there were no microservices running, all the messages, all the events were going to get buffered by RabbitMQ in our case, right? So RabbitMQ is buffering those messages and will dispatch them as and when a microservice comes up. But in case of requests, plain HTTP requests, there's nobody to buffer those for us. Most API gateways don't really do that. And definitely Cater chose not to do that either. So scaling based on request is a tough spot for Cater, and they've actively made a decision that they don't want to. Now, I know that this is sad news, but obviously you can still use this feature, because we implemented that in Space Cloud. So we really loved Cater so much, and we thought that Cater should be there in every Kubernetes system, that we added first class or native support for Cater. So now we natively support Kubernetes, which we always did. We support Istio, which we already did. So you get a service mesh by default, and you get Cater support as well now. So you can scale based on all Cater metrics through Space Cloud itself. You don't really have to worry about Kubernetes or writing Cater config files or any of that. Plus, you get scaling based on incoming requests. And the way Space Cloud really does that is that all the incoming messages which are coming are not passed to your service directly. It actually flows through our gateway. And what the gateway does is it's smart enough. It's Kubernetes aware. So it knows how many instances of your service is running. And if the number of instances is 0, it's going to hold on to it. And it's going to give Kubernetes a command to scale it up from 0. To be more specific, it's going to give Cater the command to scale it up from 0. Cater will then scale it up from 0, and the HPA will kick in from there. So the first request has a bit of a cold start to it, because upscaling in Kubernetes is slightly slower than upscaling in AWS Lambda. And but this is really beneficial, especially when you have internal events to be processed asynchronously. So your client doesn't really care about when the event get processed. It's happening asynchronously in the background. So that's really the use case of event triggers. We're trying to make all the processing happen asynchronously without having to front end to wait on it. Or should I say, we don't want synchronous events anymore. And yeah, that's what Space Cloud does for you. I think we just got a question. What are the Kubernetes objects do we need to extend or modify for Cater? And that's a good question, very relevant as well. So in Cater, you have to modify 0 existing objects. So if you have a deployment, if you have a stateful set, you do not need to modify them at all. If you have an HPA already running, yeah, you need to delete that because now Kata is going to kick in and create an HPA object for you. So if you have a deployment already running, if you have like a source of events, maybe like RabbitMQ or Prometheus, whatever, which Kata supports, you don't need to modify your deployments at all. Instead, inside of Kata's config, you just point towards the deployment, similar to what you would do for the HPA. But instead of just pointing towards the deployment, you also point towards your event source, which could be RabbitMQ for that matter. So the only config you're technically creating is the Kata config object. None of the existing config objects need to be changed at all. And that's the non-intrusive behavior of Kata, that you do not really have to change the core or the config files of your existing deployments or stateful sets which have already been deployed. And yeah, thank you guys. Thanks for bearing with me. I really try to keep it short because I think we've even overshot a little bit. So yeah, you can find me on Twitter. I am your tech bud. And if you have any questions, feel free to reach out there. Or if you're more comfortable with LinkedIn, my LinkedIn link is right there as well. And in a short while, we'll also start creating a lot of blog posts and videos on subjects like these, especially to build scalable apps with ease. So if you're interested in that, you should probably follow me on Twitter. I'll be posting all those updates right there. And of course, if you think Space Cloud is cool, if you think you really want an open source Firebase which can work with any database, if you really want to use something which abstracts Kubernetes so you don't have to worry about it, give it a try. Just to be clear, because Kata just launched its new version 2 days back, the support for Kata in Space Cloud is still not released yet. It's due to be out next weekend or probably the week after that. So yeah, just keep an eye, maybe watch it, give us a star, fork it. Would love your love, so to speak. And yeah, thank you, Prakash and Suraj. I mean, it's always great of coming here, and thank you so much for having me, guys. I think there's one question.
Yes, I was going to point it out to you. So there's one more question by Giri Prasad.
Okay. HPA with custom metric API does the job, right? How Kata is different? That's a very good question, because we technically had done the same thing. So we really had scaling based on requests per second before even we added the support for Kata. And one way to do that is really adding custom metrics to Autoscaler. And that works. So if you're really comfortable in writing your own custom metrics API, go for it. Okay. But if you really want to use an existing tool which does that out of the box, which has been tested by some of the big guys out there, and has a ton of scalars which are already pre-written for you, you probably want to use Kata. So what you did right now is a classic case of how Kata was perhaps born. Now, I'm not sure how it really went down, but people were writing custom metrics API and adding them to, pointing the HPA to them in order to scale. But obviously, you have to write code. You have to write those metrics API again and again. Kata just automates all of that. So it's exactly what you're saying. It's very simplistic. And I really think a project like this need more awareness. And that's the reason why I really chose that, maybe we should speak about it in this meetup. So yeah, a simple answer to your question, custom metrics API can do the job. If you prefer writing code, maintaining it, making sure you fix all the bugs, go ahead, do it. If you want to use something which is already written and probably works with most of the use cases out there, choose Kata. That's it.
Yes.
Over to you, Prakash.
Yeah, that brings us to the end of this as well. So the parting notes will be shared by Suraj. Thank you so much, Noreen. As always, it's great having you here, and the talks are always so interesting. The energy with which you talk to the audience is great. So yes, it's over to you, Suraj.
Sure. Yeah. Thanks. Yeah, like Prakash said, like I learned a lot, especially with this talk. I learned that like you don't need to create your own custom metrics. Now you have. If I draw parallels between Prometheus and the custom metrics exporter that people write, so Kata has done that. And in terms of the previous talk, I have drawn parallels there as well, like as in instead of just getting an alert and then doing stuff yourself, I think you can use the project from Ravi's talk to like go beyond just getting alerts and doing stuff automatically. So yeah, I think today's was a good meetup. So before we end, I would like I would request the speakers to maybe like share your presentations with us or tweet it out or whatever is comfortable for you. And yeah, we request everyone who is here. If you're not on Kubernetes Slack, please go to slack.kats.io and please join there. You can find us. You can find these the authors or the people who are contributing to Kubernetes upstream and all the related projects in the peripheral. So join there. You can find India-related, like the banner says, India-related channels in -dev or in -users or in -events. Like today's meetup was posted on in-events and yeah, and any new developments that you'll find, like anything like doing events or like last time we did Kubernetes forum, you'll find all that information on these channels. All right, so that being done, like I would request all the attendees to please give us feedback, like what you feel, what you want, like to see, what formats you want to see, and stuff like that. Like we are on KTSBLR. You can reach out to me on Slack at Suraj D, and yeah, so feedback is always welcome. And our Twitter handle, as the banner says, KTSBLR Kubernetes Bangalore, and reach out to us for whatever it is. Please submit talks if you have if you have any ideas. Please reach out to us. We are always looking for speakers, and we do them. We do these meetups monthly, so there's always a slot. And like yeah, to end this to end this on a note or like a proper YouTube channel, please like the video, share the video, subscribe to the channel, so that like next time you are when the event is scheduled, you will see the reminder. So yeah, thank you.
Thank you.
Thank you, guys. Great being here.
Thank you. Thank you for hosting. Thank you so much.